if the alternating series, the sum from n equals 1 to infinity of minus 1 to the power n minus 1 times some bn, bn's a sequence, which equals b1 minus b2 plus b3 and so on, minus b4 plus b5. What that means, you can see this is positive, negative, positive, negative, positive, negative. When we say alternating series, the things that alternate are the signs, so plus, minus, plus, minus. The thing that makes that alternating happen is this bit here, is minus 1 to some power. Now, it doesn't necessarily have to be n minus 1. If we think about minus 1 to the power n minus 1, we take n, which would be 1, 2, 3, 4, and so on. So if we had minus 1 to the power n minus 1, well, minus 1 to the 1 minus 1 would be minus 1 to the 0, which would be 1. Minus 1 to the 2 minus 1 would be minus 1 to the 1, which would be minus 1. Minus 1 to the 3 minus 1, minus 1 squared would be 1. And you can see it's going to do that. But you could also have an alternating series that looks something like that, something like this. So minus 1 to the n, well, that would be minus 1 to the power 1, which would be minus 1. Minus 1 squared, 1, minus 1 cubed, minus 1, 1, minus 1. So, yes, you could always define them with this minus 1 to the n minus 1, because if you think about the first one, if I just had a sequence that started negative and then positive, then negative, we could just multiply every single term by minus 1, and that would flip the signs around anyway. Remember that minus 1 to a power, all it does is dictate the sign. It doesn't change the sizes of the numbers at all. So if the alternating series, the sum from n equals 1 to infinity of minus 1 to the power n minus 1 times some bn, so bn will be a sequence with a different rule. If it satisfies these two conditions, so firstly, all the terms in bn, so ignoring the minus 1 to a power bit, need to be non-negative, so greater than or equal to 0, and the next term, bn plus 1, always needs to be less than or equal to the current term. So you need to satisfy that. So basically, terms are getting smaller. And if that's true for all positive integer z, so the natural domain of the series, and also if the limit as n approaches infinity of bn, remember bn is just the sequence part ignoring the signs, if that equals 0, then the series converges. So it's much easier than trying to show that the other series converge. So here we have an example. We need to show that 1 minus a half plus a third minus a quarter plus a fifth minus a sixth and so on converges. And actually, they've been very kind to us. They've given the alternating series form, but there's no obligation for somebody to do that. You could easily have to do that yourself. But they're saying this is minus 1 to the power n minus 1, which means the sign of the first term is positive, then the next term is negative, and then positive, and then negative, over n. So that could be written as minus 1 to the power n minus 1 times 1 over n, which would make your bn 1 over n. So let's write that down. So we have the series from n equals 1 to infinity of minus 1 to the power n minus 1 times 1 over n. Now, this is kind of like an alternating harmonic series. If you think about the harmonic series, which is basically exactly the same series but without the minus 1 to the power bit, that doesn't converge, even though both conditions would be met if it was alternating. So if you think about it, 1 over n, well, it is always getting smaller because n is always getting bigger. And also the limit as n approaches infinity of 1 over n is 0. But the normal harmonic series does diverge. But we will see in a minute that if we've got an alternating series, so yes, it's the harmonic series, but each term changes sign, then actually this will converge. So if we just consider the bn bit, this is bn here. So we need to show two things. We need to show that bn plus 1 is always non-negative, and it's always less than bn, or less than or equal to bn for all positive integer n. So b n plus 1 would just be 1 over n plus 1. So you know that n plus 1 is greater than n for all positive integer n. So that must mean if we take reciprocals, 1 over n plus 1 is less than 1 over n for all positive integer n. And also, because we're dealing with positive integer n's, then when we take the reciprocal of that, it's always going to be positive as well. So we can put this is greater than 0. So this is enough to show that bn plus 1 is always non-negative and it's always less than or equal to bn. So that's the first criterion of the alternating series test to show convergence. The second one, we need to consider the lim as n approaches infinity of bn. Bn is just 1 over n. And that's definitely 0, of course, as n approaches infinity, 1 over n approaches 0. So that shows us that the lim as n approaches infinity of bn equals 0. So now if we go up, we can see that we've met both criteria. Okay, so we've shown this to be true, and we have shown this to be true. And we knew that it was an alternating series. So now, by the alternating series test, this series is convergent. So, therefore, the sum from n equals 1 to infinity of minus 1 to the power n minus 1 over n converges. And the reason why we know this is the alternating series test.